So the equilibrium constant for NERNST equation is E naught cell is equal to 2.303 by RT by NF log Kc. So this Kc is the equilibrium constant. So when comparing these two equations, what I can say? Here the LHS is equal, hence my RHS will be also equal to each other. Delta G naught is equal to minus 2.303 RT log Kc. So this gives the relationship between Gibbs free energy and equilibrium constant. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 3 of the chapter Electrochemistry. So in the last session we studied about what is electrode potential, and then we studied about standard hydrogen electrode as well, She, yes, which is used as the standard electrode, right? And then we studied about the electrochemical series as well, and we begin with the NERNST equation. That is, we studied what is the NERNST equation and the importance of it. So in today's session, we are first going to continue with the NERNST equation, and then we'll study, that is the thermodynamics of NERNST equation. First we will be beginning with, and then we'll continue with the next type of the cell, that is electrolytic cell. So till now we were discussing about electrochemical cell, right? So now after this we will be discussing about the electrolytic cell as well. So now beginning with the first topic, that is the thermodynamics of NERNST equation. So how we can rearrange the NERNST equation in terms of equilibrium constant for a cell reaction. So we are going to relate NERNST equation with the equilibrium constant. Then we'll be doing with the work done by the cell as well as Gibbs free energy of the cell. So we will be connecting the NERNST equation with, that is our E naught cell, right? The electrode potential of the cell under standard conditions with equilibrium constant, work done by the cell and Gibbs free energy of the cell. So this is called as the thermodynamics of NERNST equation, right? Gibbs free energy, work done, the equilibrium constant, all this comes under thermodynamics. So that is why it is called as thermodynamics of NERNST equation. So the first relationship is between the E naught cell, that is the standard electrode potential, and the equilibrium constant, right? So the equilibrium constant for NERNST equation is E naught cell is equal to 2.303 by RT by NF log Kc. So this Kc is the equilibrium constant. So how do you write Kc? What is Kc actually? Equilibrium constant. So if I am considering a reaction AA plus BB giving CC plus DD, I am considering this particular reaction. Okay, that is A moles of A, B moles of B gives C moles of C and D moles of D. Then how do you write the equilibrium constant? It is C raised to C into D raised to D divided by A raised to A into B raised to B. So this whole part, that is this whole Kc, is written as Kc here. Okay, so this is the equilibrium constant. This is how you calculate. That is the product of the concentration of the products raised to the power of their number of moles divided by the product of the concentration of the reactants raised to their respective number of moles, right? So that is how you calculate the equilibrium constant. So this is the relationship between E naught cell and Kc. What it is? E naught cell is equal to 2.303 by 2.303 into RT by NF log Kc. So R stands for the universal gas constant, T is the temperature, N is the number of moles involved in the reaction, and F is the number of Faradays or Faraday's constant, that is 96,500 coulomb. We have already studied this. And log Kc. Kc stands for again the equilibrium constant. So this is a very, very important equation which is important for the numericals. So now moving on to the next equation, which is the relationship between E naught cell and Gibbs free energy. So the electrical work done is the product of the potential difference and the charge that flows. Okay, so how do you calculate the work done first? It is the product of the potential and the charge. So as you can see, W is equal to E cell into charge. It is the potential into charge that flows. So the maximum work done on the surroundings is equal to the decrease in free energy. And also we know that W is equal to minus delta G naught, where this delta G is Gibbs free energy, right? And G naught stands for under standard conditions. So from these two equations we can see W is equal to E cell into charge as well as W is equal to minus delta G naught. So when comparing these two equations, what I can say? Here the LHS is equal, hence my RHS will be also equal to each other, right? So that means, can I write delta G naught minus delta G naught will be equal to E cell into charge? Can I combine these two equations and write like this? Right. So that is what is shown here. So now the charge also has to be considered, which is equal to NF. Now N stands for the number of electrons which is involved in different reactions. So in different reactions, the number of electrons which is involved will be different. So it is always not 1 farad. It can be 2, 3, 4, right? The farads can differ, right? So that is equal to NF. Even this we have to include. So finally the equation will be minus delta G naught is equal to, or else you can write the minus on this side as well. Delta G naught is equal to minus NF. Yes, this NF is a constant, and then E naught cell. Okay. So finally, what is the equation? Delta G naught is equal to minus NF E naught cell. So this is under standard condition. If it is not under standard condition, we can write delta G is equal to minus NF E cell. Minus NF E cell. So this is the equation relating between E naught cell and delta G. Okay. So we studied the equation relating between E naught cell and Kc, that is equilibrium constant, and then we studied the equation relating between delta G and E naught cell. So these two equations are very important for your numericals as well, right? So now moving on to another equation in which we are going to relate between Gibbs free energy and equilibrium constant, right? We studied the equation relating E naught cell and Kc, E naught cell and delta G. Now we are going to relate delta G, that is Gibbs free energy, as well as the equilibrium constant. Okay, so we studied the equation E naught cell is equal to 2.303 RT by NF log Kc. Relation between E naught cell and Kc. This we already studied. And we also know that E naught cell is equal to minus delta G naught by NF. So I got it from this equation itself. That is delta G naught is equal to minus NF E naught cell. This is the equation. So I want it in terms of E naught cell. So I am keeping the E naught cell there itself. E naught cell will be equal to, if I am keeping this here, this minus NF comes to the denominator. Here it was in the numerator. When it comes to the other side of the equation, it will come in the denominator, right? So it will be delta G naught by NF. And this negative sign also will be there. So this is how I obtained this equation. E naught cell is equal to minus delta G naught by NF. Right. So now what I'm going to do is, here also it is E naught cell, here also it is E naught cell. LHS is equal, hence my RHS will be also equal, right? So what I can write, minus delta G naught by NF will be equal to this one. That is 2.303 RT by NF log Kc. Right. So this NF and NF is same. So I can cancel it. So what will be my final equation? Delta G naught is equal to minus 2.303 RT log Kc. So this gives the relationship between Gibbs free energy and equilibrium constant. So we studied 3 equations which is of very importance. Right. So now after studying the equations, it is also important to understand the sign conventions, right, which we have to use in different conditions. So when delta G naught is less than 0, K will be greater than 1, right? As you can see, delta G naught is equal to minus 2.303 log Kc, right? So it is negative. So if delta G naught is less than 0, your K will be greater than 1 and E naught cell will be also greater than 0. Hence, we'll say the reaction is spontaneous. So to check whether a reaction is spontaneous, always your delta G naught value will be less than 0. Always it will be less than 0, or E naught cell value will be greater than 0, or K value will be greater than 0. That is your equilibrium constant. Now, if the reaction is at equilibrium, delta G naught will be 0 as well as the E naught cell will be also 0. But your equilibrium constant value will be equal to 1. Why? Because the product concentration and the reactant concentration will be equal. So, how do you write Kc? It is product of the concentration of products divided by product of the concentration of reactants. If both of them is equal, we get the value as 1, right? So that is at equilibrium, the Kc value will be equal to 1. And if the reaction is non-spontaneous, delta G naught value will be greater than 0 and K value will be less than 1 and E naught cell will be greater than 0. So what you have to remember, for a spontaneous reaction, the Gibbs free energy will be always less than 0. For a non-spontaneous reaction, it will be greater than 0, and at equilibrium, it will be equal to 0. So I hope the reactions and the sign conventions is clear for you. So I hope the different 3 equations as well as the sign conventions is clear for you. Right? So now moving on to the next important part of the chapter, that is electrolytic cell. So till now we studied about electrochemical cell, in which chemical energy is getting converted into electrical energy. That means chemical reactions will take place, hence electrical energy will be produced. Now what is electrolytic cell? The exact opposite will take place, right? That is, electrical energy must be produced, then and then only will be the chemical reactions takes place, right? The electrical energy should be produced then or given, then the chemical reactions will take place. It converts electrical energy to chemical energy. So that means we have to supply the electrical energy, then only the chemical reactions will take place. And in electrolytic cell, the anode and cathode, the sign is different, right? It is exactly the opposite. Anode is considered as the positive electrode and cathode will be the negative electrode. But still at anode, always oxidation will take place, and at cathode, reduction will take place. No confusions in that, but the charge keeps changing. In electrochemical cell, anode will be negative, cathode will be positive. In electrolytic cell, anode is positive and cathode is negative. But in anode, always oxidation takes place, cathode always reduction takes place. So this is the basics of electrolytic cell. That is, electrical energy is converted into chemical energy. Right. So now what is electrolysis? Before understanding electrolytic cell, we need to be knowing what is electrolysis. Right? What is electrolysis? The decomposition of electrolyte solution by the passage of electric current, which results in the deposition of metals or the liberation of gases at the electrodes. So as I said, in electrolytic cell, what we are doing? Electrolysis is happening. That means we are supplying electrical energy. Yes, and using this electrical energy which is passed through an electrolyte solution. Electrolyte solution means it must conduct electricity, right? So it is passed through an electrolyte solution, and by the passage of electric current, what happens? Which results in the deposition of metals. Either some metals will be deposited on anode or cathode, right? And another possibility is there, that is a liberation of gases. So either deposition of metals or liberation of gases at the electrodes will take place. So this process is called as electrolysis, and this happens by the passage of electric current through an electrolyte solution. Okay, so I hope it is clear. So now let's understand the apparatus of it. So we have studied electrochemical cell, in which we had 2 half cells. But in the case of electrolytic cell, you only have a single cell here, in which your both anode and cathode is dipped. So you have an electrolytic solution here, and then you have a anode which is positively charged, and you have a cathode which is negatively charged. At anode, oxidation takes place. At cathode, reduction takes place. Okay, so I hope it is clear. So both of them will be present in the same cell, and if I have taken copper as the electrode, then my electrolyte solution should also contain an electrolyte containing copper. So if I am taking copper as the electrode, my electrolyte solution must be copper sulfate. Right. So I hope it is clear. So this is the basics about electrolytic cell. So now where exactly is this electrolytic cell used? Where exactly is this electrolytic cell used? So one application of this is electrolytic purification of copper. It is used in the purification of copper. So how does this work? Let's understand. So we have to take a impure copper rod, right, which is taken as an electrode. From that we have to obtain the pure copper. So that is what is called as purification. From impure copper we are going to make pure copper. So that is called as purification. So as you can see here, the impure copper or any impure metal which we are taking, which we have to purify it, that must be taken always as the anode, right? So the impure copper will be taken as the anode, and the pure copper will be taken as the cathode. So always the impure metal is taken as the anode. Okay, so as I said, in anode, what is the reaction which is taking place? It is oxidation. So what happens is, from the impure copper electrode, yes, oxidation takes place. So at the anode, what reaction is taking place? It is oxidation, right? At the anode, oxidation takes place. And what happens is, Cu, it is getting oxidized into Cu2 plus and 2 electrons. So copper undergoes oxidation and forms Cu2 plus ions, right? So this happens in the anode, and the Cu2 plus ions is getting deposited, or it is released into the electrolyte solution. So we have taken the metal salt solution itself. That means let's take the example of copper sulfate itself. So I have taken copper sulfate as the electrolyte solution. And now what happens? From the anode, Cu2 plus ions is being released into the electrolyte solution. So now what is left behind? The electrons are present in the electrode, right? And now coming on to my cathode, what will be happening? Now the Cu2 plus ions will accept the electron and form pure Cu. Okay. So in the cathode, what reaction takes place? The copper 2 plus ions will accept the electrons and form pure copper. And where this will be deposited? The pure copper will be deposited on the cathode. Okay. So in anode, we take the impure copper, and what happens? Oxidation takes place and it releases Cu2 plus ions to the electrolyte solution, and that reacts with the electrons, and pure copper will be deposited in the cathode. Yes, and where you will be able to find the impurities which were there in the impure copper. Yes, that will be present below here. The impurities will be collected just below the anode, and that is called as anode mud. That is called as anode mud. So the impurities will be deposited below the anode, and the pure copper will be deposited towards the cathode. So as the reaction proceeds, what will happen to the size of anode and cathode? Yes, here it is continuous oxidation is taking place. The Cu2 plus ions is being released. So the size of anode gets smaller and smaller, and the size of cathode will get bigger and bigger. Yes, it will become large because copper is getting deposited, right? Initially, this was big and this is small, as you can see here, because this is impure and this is pure, right? So now what happens is, as the reaction proceeds, the impurities is deposited here, and only the pure copper will be deposited in the cathode. So this becomes small and this will become bigger, right? So this is the purification of copper. So I hope it is understood what reaction is taking place in the anode and what reaction is taking place in the cathode, right? Now there is one more application of it, that is the electroplating. Now what is electroplating? We use a metal to deposit it on another metal, right? It is the deposition of a particular metal on another metal, electroplating. Right. So we have seen gold plated, silver plated ornaments, right? So gold and silver, the metals are deposited on some other metal. So this also happens through the process of electrolysis using electrolytic cell. So now let us see this particular example which is shown here. I have to electroplate a key which is present here using copper. So that is my aim. So I take the impure copper as anode again, and the pure metal, that is whichever object I want to electroplate, that I will take it as the cathode. So as we studied earlier, anode will be undergoing oxidation. So again the same reaction will be taking place. We are taking copper itself, right? So anode oxidation takes place. So Cu will get oxidized into Cu2 plus copper ions, and 2 electrons will be released. Now in the cathode, what will be happening? Yes, again the reduction will take place. So the Cu2 plus ions will accept the electrons and form Cu. So you get the pure copper which will be electroplated on the key. Right, and the impurities will be deposited here, and the pure copper will be electroplated now on the top of the key. So this is how you electroplate it. Now in this example, I have taken a key. So any other metal to which you have to deposit it, that must be always taken as the cathode, and which metal which you have to deposit, that has to be taken as the anode. Right. If I want to deposit copper on the key here, copper must be taken as the anode, and which object I want to deposit it, electroplate it on, that must be taken as the cathode. So I hope it is clear. This is how electroplating is done, right? So I hope it is clear, the electrolysis and the applications of it as well. The electrolytic cell, the applications as well. I hope it is clear. So now let's move on to the next concept, that is the quantitative aspects of electrolysis. So now what is quantitative aspects? It means now we are going to study about how much amount of the substance is liberated or deposited. Quality means whether to check whether some presence of the substance is there or not, right? Detection of various substances. But quantitative means we are measuring the mass or the amount of substance as well. So to understand the quantitative aspects of electrolysis, we need to be knowing Faraday's laws. Okay, so there are two laws which were formulated by Faraday. So let's understand the first one, that is Faraday's first law. So the amount of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. Okay, so how much amount of substance is deposited or liberated? It can be either deposited or liberated. So how much amount of the substance is deposited or liberated is depending upon the quantity of electricity which is passed through the solution, electrolyte solution, right? So if you are considering Q as the mass of the substance, right? How much mass of the substance is deposited is directly proportional. Okay, I can write it as M or Q. So the mass is directly proportional to the amount of current passed through it, electricity passed through it at a given time. So that is this equation which is shown here. Q is directly proportional to I into T. So to remove the proportionality, I write Q is equal to ZIT. So now what is Z? Z is called as the electrochemical equivalence. Okay, so Q is equal to ZIT. That is the Z is known as the electrochemical equivalence. So then how can I define Z? It is the amount of substance deposited by 1 ampere current which was passed for 1 second. So I can write Q is equal to Z when my I is 1 and T is 1. Yes. So then what? If I and T is equal to 1, my Q will be equal to Z. So how can I define electrochemical equivalence? It is the amount of substance. Q stands for the amount of substance, right? It is the amount of substance which is deposited or liberated when 1 ampere current is passed through the electrolyte solution for 1 second. So this is the definition for electrochemical equivalence, and this is the equation for the first law of Faraday. Yes, Faraday's first law, that is amount of the substance deposited or liberated is directly proportional to the amount of electricity which is passed through the electrolyte solution. So it is based on the amount of electricity which is passed, right? Now, the amount of electricity required for oxidation or reduction depends upon the stoichiometry of the electrode reaction. So the amount of electricity, yes, it actually depends upon the stoichiometry of the electrode reaction. So let's understand what is that. So the charge on one electron is equal to 1.6 into 10 to the power minus 19 coulomb. We already know this. What is the charge of one single electron? It is 1.602 into 10 to the power minus 19 coulomb. Yes, and therefore charge on 1 mole of electron will be, yes, multiply it with the Avogadro number, right? 6.022 into 10 to the power 23. This is Avogadro number into 1.602 into 10 to the power minus 19 coulomb. So we got the charge for 1 mole of electron. What is it? 96,500 coulomb, which is equal to 1 F. Now this F is called as Faraday. So what is the value of 1 Faraday? Faraday's constant, it is equal to 96,500 coulomb, right? So it is actually 96487, which is the value, but you can round it off and use it in the equations as 96,500 coulomb. Okay, so this is a charge of 1 mole of electron. So if there is different substances based on the chemical reaction or the stoichiometry, the Faraday value will be also changing, right? Yes, so if it is, let's take the example of silver. Okay, so silver is getting ionized into Ag plus and 1 electron. So in this case, yes, how many electrons are involved in this reaction? Only 1 electron, right? So in this case, it is 1 farad of current which is used. Okay, so it is based on the number of electrons and the stoichiometry of the reaction, right? So this particular number you have to remember it. 1 Faraday is equal to 96,500 coulomb, and the quantity of electricity will be equal to N into F. Now this N stands for the number of electrons which is involved in the chemical reaction. When we do a problem based on it, you will be more clear with that. So this is the first law of Faraday's. Now moving on to the second law, when same amount of electricity is passed through different electrolyte solutions, then the weight of the substances deposited or liberated at electrode are proportional to their equivalent weights. So now we are taking two different electrolyte solutions, okay, not a single one, two different electrolyte solutions, but I am passing the same amount of electricity to both. Okay, two different electrolyte solutions and passing the same amount of electricity through both. Then the mass or amount of the substance deposited or liberated is proportional to their equivalent weights. Okay, that is, if I am taking the mass deposited at the first electrolyte solution is W1, that will be directly proportional to its equivalent weight, and W2 will be directly proportional to E2. Mass deposited on the second electrolyte will be directly proportional to its equivalent weight. So together can I write W1 by W2 will be equal to E1 by E2. So this is the equation for the second law of Faraday's second law. Okay, so W1 and W2 stands for the masses or mass of the substance which is deposited in the first electrolyte solution, second electrolyte solution, and this is the equivalent weight of the first one and equivalent weight of the second one. Clear? So now what you have to remember, the first law says that the mass deposited or liberated is directly proportional to the quantity of electricity which is passed through the electrolyte solution, and the second law states that if we are taking two electrolyte solutions having two different electrolyte solutions and passing the same amount of electricity through both, then the mass deposited or liberated will be directly proportional to their equivalent weights. So we can write it in this form as well, which is important for your numericals as well. So now let's do a problem based on this. A solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 ampere. What is the mass of copper deposited at the electrode? Okay, so the solution of copper sulfate, it is given which substance, which is the electrolyte, it is given copper sulfate, electrolyzed for 10 minutes. It is given in minutes. So our first job is to convert it into seconds, right? So that is 10 into 60, that is 600 seconds, right? Now, with a current of 1.5 ampere. So, the current, that is I is also given, that is 1.5 ampere. Now, what is the mass of copper deposited at the electrode? We have to find the mass of it. So, it is, the time is given, the current is also given. So, now the electrolyte which is given is copper sulfate. So, we need to be knowing what is the equation or the reaction that is taking place. What is happening? Cu2 plus accepts 2 electron and forms Cu. This will be the reaction that is taking place. So, what we are going to calculate is the mass of Cu which is deposited. Okay. So, what is the number of electrons which is involved here? It is, yes, it is 2. So, what will be the quantity of electricity? The quantity of electricity which is required is N into F. That means 2 farads of electricity is required, right? So, as I told you, it depends on the number of electrons. So, in this reaction, 2 electrons are involved. So, you require 2 into 96,500 coulomb of charge. Okay. So, 2 into 96,500 coulombs of charge if I am taking, how much copper will be deposited? It will be 63 gram of copper which will be deposited. You have to do the problem in this way. 2 into 96,500. Why 2 into 96,500? Because it is not 1 farad, it is 2 farad based on the number of electrons which is involved in the reaction. So, 2 farads of electricity if I am using, 63 gram of copper will be deposited. 63 gram of copper means, yes, it is the atomic mass of copper, right? So, 2 farads of electricity will give me 63 gram of copper. So, now we have to see how much charge is involved in this particular reaction. How do you calculate it? Q is equal to I into T. Yes, Q is equal to I into T. So what is I? 1.5 into time is 600. So that will give you 900 coulombs. Okay, so Q is 900 coulombs. So 2 into 96,500 coulomb will give me 63 gram of copper. Then 900 coulombs will give me how much of copper? How do I calculate 63 divided by 2 into 96,500 into 900. So this is how I can calculate, right? If this much, that is 2 farad of quantity of electricity gives me 63 gram of copper, then 900 coulomb, which is calculated from the equation, 900 coulomb, how much it will give? 63 divided by 2 into 96,500. This divided by this multiplied by 900, right? So the final answer will be 0.2938 grams of copper. So we got the answer. The question was to find how much mass of copper will be deposited. That is what we have calculated now. So I hope it is clear. So I hope electrolysis and electrolytic cell is clear for you and the different applications of it, as well as the Faraday's first law and Faraday's second law, and the numerical is also clear for you. So in the next session, we will be discussing about products of electrolysis. We will going into the further details of electrolysis. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.